Hello students, welcome back. The final topic here is Cauchy-Schwarz inequality. Let V be a scalar product space, which means a vector space with scalar product. And for any V and W, the absolute value of the scalar product is less than or equal to the product of the norms. Where do you use it? One of the application is this, the subadditivity of the norm, or triangle inequality, because this is one side, and then this is sum of the other two sides of the triangle. And the proof is like this. Sub from left-hand side squared, that is equal to the scalar product of itself, and then for it, and then these middle two terms, you can write those as twice of that dot product, and then this one and that one stay the same, and this part you replace it with the product of norms. And if you use Cauchy-Schwarz inequality here, the product of norm is bigger. You see, this is the scalar product, and the absolute value is even bigger, at least equal than this, and the product of norm is even bigger. At least they're equal. So we ended up with increasing this. And then if you look at this entire thing, what do you get? We have complete square, and that's the right-hand side square. So that completes the proof of this subadditivity. Now from here to there, you may be able to use this to, V dot W, no, never mind about 2, is equal to size of V times size of W times cosine of the angle theta, and size of V times size of W times the cosine of theta can reach the maximum 1, so you may be able to use this to move from here to there. If this is big if this makes sense. If you have angle, yes, you can do that. If you do not have the angle, if you do not have any geometrical meaning of it, then this could be meaningless. We have a problem. So how do you go from here to there? And that is going to be answered from this. And Cauchy-Schwarz inequality will be proved only using the basic properties of scalar products. Let's see. Oh yeah, okay, these. Or the properties that were generated from those. Let's see, we did this already in section 1. And in section 1, we used the property of quadratic expressions, and you use the discriminant. Here, we're going to use the orthogonality, especially the Pythagorean law. Shall we begin? Okay, here we go. Let's consider a special case. If W is a zero vector, then basically there's nothing to do. And if this is 0, then left-hand side is 0, the right-hand side is always 0, so no problem there. Assume W is not 0 so that we can consider, there are too many fractions, let me increase the font. We can consider the orthogonal component so that we have W dot W in denominator makes sense. Okay, if you do that, and C is the parallel component. Parallel component, and then consequently V is perpendicular to V minus CW. So here in, is it this one? Yes, okay, it's this one. Here, we talk about this Brown vector. V minus CW. So that's a Brown vector. So V and V minus CW are perpendicular. Now these are perpendicular, so we can use Pythagorean theorem. How does it work? Here we go. Norm of V squared, you can write it as V minus CW plus CW. Okay, so far so good. We subtracted and added the same thing, so I didn't change anything. Equivalent to adding 0, so nothing wrong. And then now we separate like this and that. Okay, V minus CW, and that is orthogonal component. Oh, excuse me, that's a typo. Sorry about that. W is perpendicular to that. I'm sorry about that. Let me go back to that picture. Okay, this is brown. V minus CW is brown, and W is this one. Those are perpendicular. Not V. V and brown, blue and brown are not perpendicular. The blue and red, or blue and green, those are perpendicular. Okay, so, all right. So V minus CW and CW, those are perpendicular, so we can separate like this. One side squared plus the other side squared is hypotenuse squared. Now here we are dropping this. This is non-negative quantity, so if I drop it, then I'm going to end up decreasing this value. That's what this inequality is all about. And then let's do a little bit further algebra here. Bring the C out, then C squared in absolute value, and of course we have W squared there in absolute value. Now please recall C is this quantity, so this quantity is squared there. And by the way, why do I need the absolute value here? C squared is, this is, oh excuse me. Okay, all right. Believe it or not, this absolute value is necessary. You see, if C is a real number, when the scalar is a real number, then it's okay to simply take C squared because that's always positive. And in undergraduate level, we're going to deal with real vector spaces only. That's okay. But if you want to take this proof and apply the same thing to complex vector spaces, then we need this absolute value there. So don't throw this one away, at least not yet. And then let's see, putting this one in, V squared it V dot W over W dot W squared. All right, and there I'm not using the absolute value notation because this is for real number arithmetic only. For complex numbers, we have some complex conjugate flying around in this expression. So things are a little bit different. Anyway, okay, here. And then let's do some brute force algebra here. V dot W squared, okay, that's the numerator. And denominator, W dot W is already norm of W squared and square again, so we have fourth power. So fourth power down here, second power here. So after simplification, we have second power down here. We're almost there. And flip over this denominator to the other side. What do you have? Norm of V squared times norm of W squared is greater than or equal to V dot W squared. And finally, removing the squared by taking square root, we get what we want. I'd like to have just a little bit more space here, just for looks. And this is the proof of, this is the conclusion of the Cauchy-Schwarz inequality. But one more thing, when do we have equality? Equality holds when we dropped this, we'll have equality when this thing is 0. So that is 0 when v minus cw is equal to 0. In other words, v and w are parallel. V and W are parallel, and that means the angle is 0 or angle is 180 degrees if you have angles, so pointing the same direction or the other direction. Or in other words, cosine of theta is 1 or negative 1. So it fits our common sense as well. Of course, we cannot really consider cosine of theta in abstract vector spaces. What I'm saying here is this parallel vector, that conclusion fits our conclusion for easier vector space where we have all those pictures and angles. Anyway, here is the proof. Here is the completed proof of Cauchy-Schwarz inequality. Which is easier? In my opinion, the orthogonality proof is a little bit easier, and that's probably why our textbook author used that proof over the other proof. But then again, we had a little bit more preparation for that proof. That's why we did 2 proofs. First proof, that doesn't have to do with all those orthogonality, and the second proof that we have to go through all this orthogonality and Pythagorean. Anyway, that completes Module 10. As for the proofs of Cauchy-Schwarz inequality, those are nice things, and if you remember, that would be great. But I'll probably never ask you to reproduce those kind of things because those exceeds the kind of level that I set for this course. At least an undergraduate level, probably not much. Okay, thank you. Let's stop here.